Now, you're probably thinking, we should take advantage of the date, Halloween. We should come up with a nice Halloween quote, something like, brains. And we can say, oh yes, it's really important to use your brain. But I didn't think that far ahead. So instead, some Chinese philosophy, Lao Tzu, who said, at the center of your being, you have the answer. You know who you are, and you know what you want. And I like this. You do know who you are and what you're capable of. And I encourage you to pursue that. It's, as I like to think of it, you really get one chance at life. You should really enjoy what you do. Find what you like and pursue that. And I hope you have a great life. Now, good news is we're basically already done. So there's not too much left for us to learn. We're just going to do some practice and make sure we know what we need to know. All right, so let's talk about a few things. Now, one thing you're going to see, and this is probably going to show up, if it hasn't shown up in your homework, it will show up in the practice exam, which means it will probably also show up in the real exam, which is you want to be able to go back and forth between systems of linear equations and matrices. And so that's a good skill to have. So what do we mean by a system of linear equations? Well, that tends to be something like what you see down here, where you have several equations written out, you have it, all the variables floating around, and you say, all right, that's my system. Well, what do we mean by matrices? Well, that's what we have upstairs. So, they look like an array or a table of numbers, but we know matrices are so much more. All right, so how do we do it? Well, if we are starting with matrices and we want to go to systems, so that's what I put this arrow here, from matrices to systems, well, the way to do it is to carry out the multiplication, and then you compare entries. So, let's just do that. So we'll carry out the multiplication. So we're multiplying this 3 by 3 matrix with this 3 by 1 matrix. And so what do we get? Well, we're going to get 3x plus 0y plus 4z. So I'll go ahead and write that out. 3x plus 0y plus 4z. X minus 2y plus 5z. And minus 3x plus 4y minus 2z. So, all right. And that's just carrying out the multiplication on the left. We still have the expression on the right. And now, that's the first step, and then there's an and, which says compare entries. Because if two of these matrices are equal, the corresponding entries have to be equal. So it says, all right, the first entries have to be equal. So that leads us to 3x, and I'll now not write the 4y. I'll go ahead and skip that. Sorry, the 0y. I'll skip that. Equals 1. So that's the first entries being equal. The second entries being equal. X minus 2y plus 5z equals 7. The third entries being equal. Minus 3x plus 4y minus 2z equals minus 6. And now we have our system. And you can probably see that there's almost, if you see the pattern, you can just jump right ahead. Because what you should see is you have this x, y, z here. And you say, that says that the first entry is x. So these parts here, these are your x coefficients in the first column. Then the second entry being a y says that the second column, these are your y coefficients. And then the third entry being a z says that your third column, these are your z coefficients. So you can see that, right? The 3, 1 minus 3, 0 minus 2, 4, 4, 5 minus 2. And you can get to the point where you can almost go straight from there to there. It's not meant to be hard. And with practice, it can become fairly automatic. All right, so we can go from matrix to system. Well, what do we do for the other thing? Well, we basically want to have the same mindset. We say, all right, let's organize. So we'll organize. Notice how when we wrote the final answer to the previous one, we lined up the X's and the Y's and the Z's. So that's what I recommend. Line them up. Okay, so what are our variables? Well, we see there's x1s, there's x2s, and there's x3s. So our variables are x1, x2, and x3. Sometimes you might see an x, y, z. Sometimes you might see x1, x2, x3. It's just different ways of writing things down. Don't be nervous about that. Now we want to line things up. So we'll follow the subscripts in terms of like, okay, what goes first? The x1s. So I have a 2x1. I'm going to leave space because there's really a no x2 term, plus 3x3 equals 4. On the next one, there's no x1 term. We start at x2 and minus 4x3, and that equals 7. The last one has all three, x1, 5x2, and plus 6x3, and that equals negative 9. Now, there's this piece of advice. Don't forget zeros. And by that, you might notice, not all the equations use all the variables. That's all right. We'll just throw them in. So, we say there's no x2, so that's like there's a 0x2 in the first equation. In the second equation, there's no x1. So that's like, oh, there's like a 0x1 floating there. Now, we say, great. What can we do? Well, once you have it in this form, you say the matrix, that comes from your coefficients. So you can read off your coefficients. 2, 0, 3. That's the first line. 0, 1, negative 4. That's the second one. 1, 5, 6. That's the third one. Now, you're going to times that by a column. Those are your variables. And you say, look, what's associated with the 2, 0, 1? That's x1. That goes first. The second column, that's going to come in the second entry. That's your x2 column. Third column, that's your x3 entries. That's the third entry. And then finally, don't forget to put the other side also into matrix form. 4, 7, minus 9. All right, any questions? Yeah, it's not meant to be hard, and it really will, with practice, become fairly automatic. Just make sure you write down symbols in the right way. If they use x1, x2, use x1, x2. If they use xy, use xy. So, all right. Well, we should do more problems. So here's a problem you might encounter where it says, solve the following system. Now, given that it just says solve the following system, there's multiple ways to approach this problem. Because there's lots of ways we've learned about solving systems. That's kind of the point of this chapter. It's like, how can you learn to solve a system? There's substitution, where you say, I can use the equations to solve for variables and plug it into the other equations. There's elimination. There's treat it as an augmented matrix. And then there's the matrix form. Now, I want to do the matrix form just so we get a little bit more practice with taking inverses. So, step 1. Let's turn this into a matrix type problem. All right. So we'll have our matrix there. There will be an x, y, z, and there will be a 1, 1, 1. Can you help me? What's in the first row of this matrix? If we use this first equation, what's in the first row? 1, negative 1, 1. All right, read off the coefficients. The second row, what's in the second row? Again, look at coefficients. What do we have?
0, 2,
Right, 0, 2, negative 1. There's no x, so treat that like a 0x. The last row, what do we have? 2, 3, 0. All right, so in the book, they like to write this as our A, matrix A, our X equals B. They like to use capital letters. I will say this becomes less common in other classes. Sometimes they'll use capital letters for square matrices, lowercase letters for column matrices or vectors. And now they say, what's the idea? The idea says if you multiply on the left by A inverse, then you'll get A inverse AX equals A inverse B. And then you say, but I can change the way I multiply this. So instead of taking AX and then times it by A inverse, I can take A inverse A and then times it by X. But this is the identity. And the identity times X leaves you with the identity. Leaves you with X. That's the power. So what's the main point of this problem or the challenge? Well, the inverse. All right. So that's our goal. Practicing finding that inverse. Well, let's begin. I don't know what the inverse is. I haven't done this problem before. We'll find out together. There's not really a great shortcut for 3 by 3. There are formulas for it, for the inverse of a 3 by 3, but at that point I think remembering it takes so much time. It's just easier to do it. And you might say, aren't calculators good at this? They are. Graphing calculators are fantastic at this, but graphing calculators aren't allowed on the exams. So you want to make sure you can do it. Of course, on the homework and quizzes, who knows what you use? We'll never know. But you want to make sure you can do it so that if you see it on the exam, and there will be at least one inverse problem on the exam. I don't know if it's 2 by 2 or 3 by 3, but you want to make sure you can do the process. All right, so what's our mindset? We wrote down our matrix we're trying to find the inverse of on the left. We write the identity on the right. Our goal is to do row operations, and we're going to make the left-hand side, which is currently A, look like the identity matrix I. And once we succeed, the right-hand side, that's what we were looking for all along. Proceed column by column. All right. So we start with the first column, the 1, 0, 2. Our goal is to make it look like 1, 0, 0. We say, all right, well, that means we want to have the entry up here look like a 1. Good news, already there. We say, okay, but we also want to make the second entry look like a 0. Okay, cool, already there. And the third entry look like a 0. Whoops, well, that's okay. We have the technology to fix that. So we're going to take minus 2 times the first row, add it to the second row. So in notation, that's minus 2 row 1 plus row 3 becomes row 3. again, I took a sneak peek at your practice exam, and one of the things that you want to be able to do is understand what this means. And so make sure you understand this kind of language. Minus 2 row 1 plus row 3, arrowing into row 3. That means we're going to take negative 2 times row 1, add it to row 3. All right, so what do we get? Well, the good news is the first 2 rows we like. So we'll stay as they currently are. So copy them down. And then the third row, we'll have minus 2 plus 2, which is 0. 2 plus 3, which is 5. Minus 2 plus 0, minus 2. Minus 2 plus 0 is minus 2. And 0 plus 0 is 0. 0 plus 1 is 1. All right. Next, we say, okay, first row, success. On to the first column, success. On to the second column. Okay, so there's our second column. Now, our goal is to make it look like this second column with the identity matrix, 0, 1, 0. So we say, okay, we want to make this entry look like a 1. It currently looks like a 2. So how do you make it look like a 1? Scale. Now, you might say, what if this had been a 0? Well, and this had not been 0. Don't forget, you always have the swap in your back pocket. So don't get nervous. There's multiple operations. All right, so we're going to scale row 2 by a half. So a half times row 2 becomes our new row 2. Okay, so the first and third rows stay as they are, and we're going to try to squeeze this in. 0, 1 minus a half, 0, 1 half, 0. 0, 5 minus 2, minus 2, 0, 1. All right. Well, we're making progress, and that's the goal. You don't have to jump from the beginning to the end. The goal is to just make a small series of steps each time we get closer and closer. And we're doing that. All right, so the next thing is we need to get the other entries, the one above it and one below it, to be 0. So we're going to do 2 row operations to get there. Row 2, add it to row 1. And then row 2 times negative 5, add it to row 3. So row 2 plus row 1 becomes our new row 1. And minus 5 row 2 plus row 3 becomes our new row 3. We're going to do those both together. Okay. Oh, exciting times. Now, the middle row isn't changing. We're just using it to help us with the other 2 rows. So we'll copy down the middle row. All right, now for the first row, we're adding the second row to the first row. So 0 plus 1 is 1. 1 plus negative 1 is 0. Negative a half plus 1 is a half. 0 plus 1 is 1. A half plus 0 is a half. And 0 plus 0 is 0. Now, for the other case, we're going to multiply by negative 5 and add down. Negative 5 times 0 is 0, plus 0 is 0. Negative 5 plus 5, 0. Negative 5 times negative 1 half is positive 5 halves. If you subtract 2 from 5 halves, what are you left with? So negative 2 is minus 4 halves, which means 5 halves subtract 4 halves is a half. All right, we still work through. Negative 5 times 0 is 0, plus negative 2 leaves us with negative 2. Negative 5 times a half, negative 5 halves plus 0 is negative 5 halves, and 0 plus 1 is 1. All right, 2 columns down. We're doing great. 1 column left to go. All right. So our goal is to make this column look like the 0, 0, 1. So we look at this and say, all right, well, what do we want? Well, this third entry down that column currently is a half. We don't want it to be a half. We want it to be 1. So what do? We scale. So we're going to take 2 times row 3. That becomes our new row 3. So that's our scaling our column. All right, so 1, 0, 1 half, 1, 1 half, 0, 0, 1, minus a half, 0, 1 half, 0, 0, 0, 1, minus 4, minus 5, 2. All right. We keep making progress. We're almost there. We're in the home stretch. So the last thing to do is to knock out the 2 entries above it. The 1 half and the negative 1 half. We want them to become 0. So, well, if we take a half times row 3 and add it up to row 2, that should do that. And minus a half times row 3, add it to row 1. So using our notation, we'll start with the top row. Minus 1 half, row 3 plus row 1 becomes our new row 1. And 1 half row 3 plus row 2 becomes our new row 2. Okay. Which gives us, if we do our job well, the last row won't change. Let's start with the top. So we're multiplying by minus a half and adding. So we get 0 plus 1, 0 plus 0, minus a half plus a half. All right, it's like we planned it, because we kind of did. Then we'll get 2 plus 1, 3, right? Because minus a half times minus 4 is 2, add up. Then we're going to get 5 halves plus a half, which gives us what? 6 halves, 3. Then we're going to get minus 1 plus 0, minus 1. All right. Now, the other operation. Multiplying by half, add up. 0 plus 0, 0 plus 1, a half plus negative a half. Good. Now, negative 4 plus 0, negative 2. Then we're going to get negative 5 halves plus a half. Negative 5 halves plus a half is negative 4 halves, negative 2. Then we're going to get 2 times a half is 1. Add it up, get 1. So, the claim is this is our inverse. All right. Now, it's okay to be skeptical. I make mistakes frequently on these kinds of things because it's just one small arithmetic mistake can derail the whole process. How can we check our answer? How can we be like, yes, this for sure is the inverse we've been looking for? Is there anything that the inverse does that's really quick to check, comparatively speaking, to what we just did? Well, the inverse, when you multiply by the original, they should undo each other. So let's do a quick check. So we'll do a sanity check. So we're going to take our A. So I'm just copying down A here. 1 minus 1, 1. 0, 2 minus 1, 2, 3, 0. And then we'll multiply it by 3, 3 minus 1, minus 2, minus 2, 1, minus 4, minus 5, 2. And what happens when we multiply? So we'll get, right, we go along the rows, down the columns. 3 plus 2 minus 4 gives us 1. 3 plus 2 minus 5, 0. Minus 1 plus 2, 0. This is looking good. 0 minus 4 plus 4, 0. 0 minus 4 plus 5, 1. 0, 2 minus 2, 0. Last row, 6 minus 6 and 0. 0. 6 minus 6 and 0. 0. Minus 2 plus 3 and 0. So we got out the identity. That means we did our job right. We don't have to wonder, I wonder if I'll get points for this problem. Like, no, we definitely can know. And it's as the great mathematical philosophers often say, you should check yourself before you wreck yourself. All right, now, are we done with this problem? No. Are we almost done? Yes. What's left? Well, not a lot of space on our paper, but the point here is all our work has been finding A inverse. So now we're ready to say, oh, that means that our x, which is our xyz, this part, is equal to our A inverse, which we just found, times our matrix, which is 1, 1, 1. So the last thing to do is carry out the multiplication. So we get 3 plus 3 minus 1, 5. Minus 2 plus 1, 3. Minus 4 minus 5 plus 2, minus 7. Or if we just compare entries, x should be 5, y should be 3, z should be negative 7. And there we go. All right. Any questions? Well, in that case, we'll do a little bit of work here. So here, our goal is to solve the following for x, y. So we can leave it as a vector. We want to get the vector x, y. And we have these expressions, and our goal is to say, okay, solve for what x, y should be. So we want to get x, y by itself. This is a practice in saying, can we manipulate these expressions? We have tools. We can add, we can subtract, we can multiply. We can multiply by inverses. Now, subtraction allows us to move things from one side to the other side. So keep that in mind. So the first one says we have 3, 1, 5, 2 times xy plus 1, 5 equals 2, 6. Channel your inner arithmetic. What is it you'd want to do? If you're trying to get this by itself, what would you be doing? And if it helps, just sort of think of an analogous thing. This is like 2x plus 5 equals 11. What would you do if you saw that kind of equation? 2x plus 5 equals 11. Well, what I'd recommend is move this across. How do you do it? You can subtract it from both sides. So 3, 1, 5, 2 xy. That's 2, 6. Subtract 1, 5. Because there's this nice fact, I should make a note here. If you take A, subtract A, you get what's called the zero matrix, which is the matrix which has 0 entries. And once you have the zero matrix, as long as the size matches, says, look, I don't do anything. You can drop me. You don't need to write me down anymore. So that's what's going on. Now 2, 6 subtract 1, 5 gives us 1, 1. All right, we have a simpler equation. Well, what can we do here? What would we want to do? Well, we want to get the xy by itself. The problem is there's something in front of it. It's like, if only we could get rid of that. Can we get rid of it? Yes, we have the technology. How do we get rid of this matrix? Let's call it A. What do you do? Well, we can multiply by A inverse. So we'll multiply 3, 1, 5, 2 inverse times 3, 1, 5, 2 xy. And that'll be equal to 3, 1, 5, 2 inverse 1, 1. But when you multiply on the left-hand side, what happens? The inverse of a matrix times the matrix becomes the identity. And if you multiply that by xy, you get xy. So we just have this little piece left. Now it's 2 by 2. We have kind of a shortcut, if you remember it, to finding the inverse of a 2 by 2. So this is 1 over, you multiply the diagonals, 3 times 2, 6, minus 5 times 1, minus 5. Then what you do is you swap the entries on the diagonal, so that makes 2, 3. And then for the off-diagonal entries, you flip the sign, so minus 5, minus 1. This is what we went through last time. We said, okay, here's the way to do every 2 by 2 matrix for the inverse. Now the good news is 1 over 6 minus 5 simplifies, and it becomes the 1. So we don't need to worry about that. So now we just multiply the matrix. 2 minus 1 makes 1, minus 5 plus 3 minus 2, and we have our answer. So subtract, multiply by the inverse, clean everything up. All right. Well, let's try this again. Part B. 2, 1, 4, 3 times the xy plus 3, 4 is 5, 1, 2, 1 times xy. How do we approach this one? You might say, if we multiply by the inverse of 2, 1, 4, 3, well, that helps us because that makes what's in front of this xy go away, but it doesn't make what's in front of this xy go away. What can we do? What can we do? Again, just think of an analogous problem. Anything with just numbers, think of that as a number. Anything with variables, think of it as a variable. All right, if you had 2x plus 7 equals 6x, what do you do? What would you do? If you had 2x plus 7 equals 6x. This is our analogy. How do you solve this? Can you solve it? I think you can. I believe in you. What would you do? What's your first step? Yeah, you'd put the x's together. You'd subtract 2x from both sides. Brilliant move. Let's do it. So we're going to take this piece and subtract it to bring it to the other side. So we get 3, 4 is equal to 5, 1, 2, 1 xy plus 2, 1, 4, 3 xy. Now, here's the thing. If you think about the problem, 2x plus 7 equals 6x, you say, well, that's 7 equals 6x minus 2x. Then what you often do is you say, oh, I'll just pull an x out so I can group the coefficients. Now, we've done it so often that we don't even think that's what we're doing. But that's what we are doing. And so when you say, oh, so let's do that here. And I should correct myself. I put a plus. We brought it over. It's a minus. Let's do that here. And we're allowed to do that. That's one of the properties of matrices. If I have a common matrix being multiplied on the right, I can pull it out on the right. So this becomes 5, 1, 2, 1, subtract 2, 1, 4, 3, times xy. Basically, matrix manipulation works just like what we're used to. There's 2 caveats. Caveat number 1, you have to make sure the size of matrices makes sense for the operation. And caveat number 2 is there's one thing that doesn't carry over. And that is the order of multiplication matters. A times B and B times A are not always the same. Sometimes yes, but sometimes no, so be careful. All right, now we can subtract the matrices from each other. So we get 5, 1, 2, 1, 5, 1, 2, 1, subtract 2, 1, 4, 3 will become, just subtract term by term, 5 minus 2, 3, 1 subtract 1, 0, 2 subtract 4, negative 2, 1 subtract 3, negative 2. xy. And now we do what we did up here. It says, oh, we really just need to multiply by the inverse. So we get that xy, and we can write this in a few steps. That's 3, 0, minus 2, inverse times 3, 0, minus 2, times xy. But we say, aha, this 3, 0, minus 2, xy is 3, 4. So we're going to have something times 3, 4. Well, what's the something? Use our rule for inverses. 1 over minus 6 subtract 0. All right, well, fractions are okay. We can live with it. Swap the diagonals, minus 2, 3. Flip the signs on the off diagonals, 0, 2. So this will become minus 1, 6, multiplication, minus 6 plus 0. Then we get 6 plus 12, 18. And you can multiply the minus 1, 6 through, and you get 1, negative 3. I'll be honest with you, I'm actually surprised this came out to a whole number, because I just randomly made this up. I was almost sure that this would come out not nice. Okay. I'm so glad it came out nice. All right. Any questions on that one? Okay. So let's turn to the third one. 5741 xy is 3xy plus 25. So this one brings in a new wrinkle in that we have 3. And so that's a scaling. We haven't done that in a little bit. So it's good to remind ourselves that we can scale vectors. All right. I will say I'm 95% sure we're going to get messy fractions on this one. But that's okay. That's life. That happens. So, what can we do? Well, let's do what we did before, right? We bring the pieces with the xy's to one side. So we'll move that over. And we're a little bit short on space, so we'll grab some paper here. And so what do we currently have? 5, 7, 4, 1, xy is equal to subtract 3, xy is equal to 2, 5. Now, we're tempted to do something, so we're going to do it. What are we tempted to do? Well, we look back and say, hey, this idea was so nice. We pulled out the xy. Let's do that. Ah, cool. Cool. Let's do that. 5, 7, 4, 1, subtract 3, xy equals 2, 5. All right. Is that legal? Can I take a matrix and subtract a number? In other words, does this 5, 7, 4, 1 minus 3, is this like okay? I'll give you a hint. There's one or two possibilities. Yes or no. So, is this legal? No, it's not. Okay, so what's the problem? Well, you can't combine matrices with numbers in this way. If you're going to do a subtraction involving a matrix, you have to have another matrix. It has to be the same size. So this is not legal. Does this mean that you can't solve this problem? No. We just have to find a way to make it legal. And there's a hint. It says, if you take the identity times xy, you get xy out. Now that doesn't seem like much of a hint, but there's a fun little fact here. So what does it say? Well, what you can do is you can add a matrix if you need one. But the matrix you add is the identity. Now you have a matrix, and so if you factor it out here, then life is good. It works. No issues. No issues at all. So we proceed as before. Don't forget to scale. So this leads to 2, 7, 0. Oh, sorry, not 0, 4. I know. 4 subtract 0. And negative 2. Right? So it's 5 subtract 3 and 1 subtract 3 on the diagonals. The off diagonals don't change. Times xy equals 2, 5. So xy, that's our 2, 7, 4, negative 2 inverse times 2, 5, which, well, the inverse 1 over minus 4, subtract 28. Then we're going to have swap the two entries on the diagonal and change the signs on the off diagonal, times 2, 5. So that becomes minus 1 over 32, minus 4, minus 35, minus 39, minus 8, plus 10, 2. So we end up with 39 over 32, and 2 over 32 makes minus 1 over 16. All right. So that's the end of our practice. It's the end of our chapter. And I just want to say before we end for the day, what are the main ideas for systems? So these are the things that we want you to be able to do. If you can do these things, it's been a success. Writing systems as matrix and vice versa, we talked about that earlier. Solving systems by substitution and elimination, that's where we started. Knowing how to perform the row operations. And also, how do you use the row operations to put the matrix into reduced form? Know what reduced form is. Reduced form is basically make as many zeros and ones as you can. The first non-zero entry should be a 1, and every other entry that you can knock out gets knocked out. This is what we call Gauss-Jordan elimination. Know how to interpret your answers. So you either get 0, 1, or infinitely many solutions. Know how to solve 2x2 and 3x3 systems. Know how to do arithmetic with matrices. That includes multiplication, adding, subtracting, scaling. And also say, hey, this is not possible, because some things aren't possible. So if you're like trying to add matrices of different sizes, you say, not possible. Know how to find your inverses for both 2x2 and 3x3. We did a 3x3 example earlier. 2x2, if you memorize the formula, great. If you memorize the process, great. Whatever works for you. And also, of course, solving systems using matrices, which we had a lot of practice on today.